Mr. McBrien, and this is a preview to organic chemistry, structure and bonding in organic chemistry. The world of organic molecules is rather interesting. There's an incredible diversity of compounds that can be achieved. It's really quite amazing to realize how many different molecules can be formed from carbon and just a few additional elements that can be added to it. If we want to revisit the periodic table to think about the elements that are of interest to the organic chemist, for the most part, we're restricted to just these usual suspects: hydrogen, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, and iodine. So this is very interesting. With just a few elements, we can form many billion different compounds. And why is this? Well, in order to get an understanding of this, really we have to dig deeper into, once again, the world of orbitals and consider the valence electrons associated with carbon. So if we start and we consider the 2s orbital, it has spherical symmetry as well as a node inside it. So this is a cutaway from the three-dimensional shape of the 2s orbital. And we can see that there are regions of low probability for that electron, but also regions of high probability, and these are arranged spherically around the nucleus. So if we want to look at this graphically, the probability equation looks something like this around the center as, once again, a cutaway. And this is interesting from the point of view of contrast with the p orbital. So the p orbital, its cutaway of the probability for the 2p orbital looks something like this. So it looks kind of like a dumbbell around the nucleus. And if we want to look at a three-dimensional representation of this, then the 2px orbital will look something like this, with a plane in between it of zero probability. And then we have to acknowledge that there are three dimensions for these p orbitals, and in fact three orbitals, and so they're arranged at 90 degrees to each other, and this is what they look like superimposed. Okay, so a pretty big difference then between the s and p orbitals. So each one of these then with a plane of zero probability that goes through the nucleus, and each of them at 90 degrees to each other. All right, now if we dig back even deeper, we can look at the electron configuration of carbon and see that we have, if we use the standard filling rules, we have something like this. Now, what's interesting about this is we have two unpaired electrons. So we'd suspect that we should see two different identical bonds that would form to fill those empty slots. Now this is where things get interesting. This isn't what we observe. So instead of seeing two bonds with carbon, and incidentally, if we were going to see more bonds, we would see something that corresponded to the filling of the Z orbital. That isn't what we see at all. We see it, that carbon wants to form four bonds, and that these four bonds are identical. So if we look at methane with its four bonds with hydrogen, we see that these bonds are in fact identical, and we have regions of the same electron density. So here's methane and its shape. Now it's important for us to remember that these straight lines represent the hydrogen being on the plane of the paper. the solid line being out of the paper and the dotted line going down below the paper. Now, whether we're talking about ammonia, water, hydrogen sulfide, all of these kind of have this, instead of forming simple systems, they form this tetrahedral angle type geometry. And the other species form this based on the idea that even the unpaired electrons repel the paired electrons, the shared electrons in the bonds. We call this geometry tetrahedral because in the case of methane, we see the hydrogens at the points of a tetrahedron, and then carbon at the center of the shape. And careful thought about this can give us the angle between here then at 109.5 degrees. This means an equal angle between each one of the hydrogens. In other words, they're equidistant from each other. And we have various representations of methane, all of which have been observed, which are inconsistent with that model of having two unpaired electrons in the px and py locations and an empty slot for two more electrons in the pz. And the answer to this puzzle is really associated with this balloon shape in the center, and that's what we'll cover now. Incidentally, all of these representations of methane are equally valid for different purposes. We have our ball and stick model, our space filling model. All of these are useful for you to be able to think about and reproduce as necessary. Okay, so this methane molecule that we've observed many, many times is inconsistent with the ground state electron configuration of carbon. So something is happening, something is going on. And really the answer lies here in this slide. So in order to form four bonds and fill its and achieve the stable octet, the ground state electrons are modified. One of the electrons is promoted from the 2s location up to the 2pz location, and we have four unpaired electrons. And even this wouldn't solve our puzzle. And the reason why is because these three p orbitals would be equivalent to each other at 90 degrees, and then there would be this other orbital with spherical symmetry. And this isn't what we observe. We observe four identical bonds in methane. So really the only theory that can solve this, this puzzle is for the 2s electron to be promoted up, hybridized with the other orbitals to form four identical bonds. And this hybridization is what results in our tetrahedral geometry. So instead of having one 2s and three 2p, we have four sp3. Okay, so this is another cartoon of what we get then. What we have are four locations for electrons to bond, each of them having some character of s and some character of one of the p orbitals. And what results then is four sp3 hybrid orbitals. And this, mathematically, gives us our tetrahedral geometry. We wind up with bonds that are in close agreement with experiment. So in the case of methane, that looks like this. with 4 hydrogens assorted around the carbon. In the case of ammonia, we wind up with 3 hydrogens around ammonia, and the unpaired electrons form the other node in the orbital picture. Now, so this does a pretty good job of explaining methane, but does it explain these larger molecules where carbon is bonding to itself? Well, in fact, it does a pretty good job of this too. So if we take our sp3 hybridized carbon, and this construct is more of a mental construct than anything else, we wouldn't see bonding like this normally. The bond would not form in this precise way. But if we have the sp3 hybridized carbon coming into proximity with the second sp3 hybridized carbon, we can see the overlap of these unpaired electrons here. And this forms what we call a sigma bond. So this is a single bond between our 2 carbons, and it's the overlap of a hybridized sp3 orbital with another sp3 orbital. And so this is the mathematical sum of these. And this explains very nicely the geometry that we see for ethane. So we see something very close to the tetrahedral angle. And if we put hydrogens at the other locations, we wind up with ethane. And if we look at the overall orbital depiction of ethane then, these sigma bonds are shorthand for a single bond. We have the overlap of sp3 in between the 2 carbons. And we have another kind of sigma bond, the overlap of an sp3 hybridized orbital with a 1s orbital to allow for the bonding with hydrogen. So this is a pretty good depiction of the bonding that we see, of the electron density that we see around ethane. Okay, but then we can begin to consider the idea of, if that's the explanation for ethane, how do we explain molecules like ethene, where we don't see tetrahedral geometry? Well, in fact, in ethene, we see only 2 bonds, only 3 species bonded to the carbon. And we'll see why in a few seconds. But when we only are assorting 3 atoms around carbon, we no longer have need for 4 locations for these, obviously. And then we see hybridization of this type. So if we're only bonding 3, we see an S hybridizing with px and py to form a different kind of hybrid orbital, an sp2 hybrid. So these look similar, but they have some differences to them. And the biggest one here is, of course, they want to maximize the distance between them. But because the z-axis is neglected, these are all in the same plane. So they maximize this distance between each other at 120 degrees, but they're all in the same plane. Now, what happens to the unhybridized pz orbital? Well, in fact, it remains unmodified from its original state, and it's above and below the plane of the molecule. So if we view it from the side, it looks like this. So what we have then are 3 hybridized orbitals and 1 unhybridized orbital. So what happens to that orbital? Well, if we want to form an atom, what we wind up doing is we wind up taking this bonding structure, and we bond 3 different atoms to the carbon using the hybridized orbitals, and the last one will form in ethylene or ethene a double bond, an additional bond. So when we move these together in this sort of conceptual exercise, if we move our 2 carbons together this time, we still have our overlap of one of our sets of sp2 orbitals to form our sigma bond, but the additional unpaired electrons overlap above the plane of the molecule and below the plane of the molecule, incidentally, to form what we call a pi bond. And this has none of this sp2 or sp3 hybridization. These are simply the overlap of 2 sets of p orbitals. So what you need to realize then is that these 2 hybridized orbitals exist in the plane of the molecule, and they could be bonding, for example, to hydrogen, and these sit above and below the plane of the molecule. We call that a double bond or a pi bond. And no great shock, the same kind of cartoon here. We have our original ground state orbitals. One electron is promoted up to the excited state in order to give us our 4 valence electrons. However, only 3 of these are needed for sp2 hybridization, so they remain in this lower energy state. And the 3rd p orbital, the pz orbital, is left unmodified. So when it comes time to talk about drawing these organic molecules, of course, it's always a challenge because they're 3-dimensional molecules, and we tend to communicate in 2-dimensional space. So let's talk for a few seconds about some representations of these orbitals that we've just seen. I'm not going to ask you to draw balloon animals too often, and so we need to see how we might communicate this kind of overlap of electrons. So we've got our classic Lewis dot diagram on the left. Usually in organic chemistry, we represent electron pairs, bonded electron pairs, with a simple line. Once in a while, we'll ignore that altogether and just simply write CH3, CH3 to represent these 2 methylene groups. Methyl groups. To represent these 2 methyl groups, it really depends on the situation involved and how, but we need to be able to mentally put these bonds in place where we need to. So we could have 2-methylbutane communicated in this manner, we could communicate in this way, or even condense it further. All of these are representations of 2-methylbutane. Now, we have already seen that the tetrahedral angle is involved for all of these hydrocarbons. So the angle between these, each one of these species is roughly 109.5 degrees. So how do we represent this? Well, when we need to, we need to realize that this dashed line means it goes below the plane of the paper. Anytime we see a simple straight line, it's flat. And anytime we have this solid wedge, it'll be up out of the plane of the paper. We often will neglect this, but when we need to be explicit about the 3-dimensional structure, this is how we do it. Often, we'll simply draw a zigzag to represent the 109.5 degrees between the carbons and leave all of these hydrogens implied. So we could have a structure like C12H26 here, and we could decide to omit the carbons, and the vertices then are simple carbons with H's written out, or we could go even simpler. So it's up to the viewer to mentally add in these hydrogens. Don't make the mistake of thinking that there are simply carbons at the vertices and no hydrogens included. If we included the hydrogen every single time, we wind up with a sea of H's everywhere we look, and it doesn't really communicate the structure any better. Okay, a few more tricks about drawing clear structures. Where you can, it's better to take the CH3 and invert it so that the carbon is what's on the bond, just to make it a little clearer to the observer. Similarly, you can invert the OH to show that it's oxygen that's bonded to carbon and not hydrogen. But we will see plenty of cases where, for example, this ethyl group will be written CH3CH2 rather than trying to make sure that the carbon touches the bond. Where you can, it's always good to write it in this kind of way, so we can see the nitrogen is attached to the carbon, and so we invert it in order to show it. Now, benzene is extra special. We'll talk about it later, but it can be drawn as either of these resonance structures, and again, we'll discuss resonance in a little bit, but these are absolutely equivalent. So when we have this alternating double and single bond in benzene, you can draw them in either way, and it's equally accurate. So this is the same as this. And in fact, many times we'll just see benzene drawn as a circle here to represent the alternating double and single bonds. So to summarize then, we've gone through a tremendous amount of information. We need to realize that the bonding in carbon is, it occurs the way it does due to hybridization of 2s and 2p orbitals to create sp3 orbitals. So when we say sp3 then, it means we have 4 bonding electrons, 4 locations for electrons to bond, to pair. And each one of those 4 has 25% S character and 75% P character. These sp3 orbitals will form single sigma bonds at the perfect angle to maximize distance between substituents. So that's just about exactly 109.5 degrees. sp2 hybridization occurs when carbon attaches to 3 different species. That's typically when there's a double bond. And in this case, the 3 species will be arranged in a planar configuration with an angle between them of 120 degrees. When you draw your organic structures, be sure that you realize that hydrogens do not have to be placed on every carbon to the right number unless a test question requires you to do so. And when you look at structures, you need to be able to fill in those hydrogens to make sure that carbon has the appropriate stable octet of electrons. Thanks very much, and have a great night.